Hi students, this is Mrs. Bogus, and this video will take you through lesson 14 of our functions unit, in which we will continue absolute value. A few expectations for the lesson before we move on. First, obviously watch this video. Second, take notes in your workbook and pause the video as needed. My presentation is going to be the exact same as what I'd like you to see in your workbook, and I would love for you to pause the video and write down things that I have on here. The third is if you are going to need any clarification, I'm going to want to see your notes first. I want to see that you've watched this video, you've written some things down so that I can know where to help you. Let's get started. Today, we will be investigating distance as a function. Our agenda is going to be to review what we did yesterday. We're talking about the distance function. We'll be moving some graphs, and then I'll give you some time to practice. In your workbooks, please turn to page 234. The first activity we will be doing is temperature in Toronto. Toronto is a city at the border of the United States and Canada, just north of Buffalo, New York. Here are 12 guesses of the average temperature of Toronto in degrees Celsius in February 2017. The average actual temperature of Toronto in February 2017 is 0 degrees Celsius. Use this information to sketch a scatter plot representing the guesses X and the corresponding absolute guessing errors Y. So this is exactly what we did yesterday in class with the guessing game of the jars. So I'll show you an example and then I'll have you pause to complete the first activity and then move on. 0 degrees Celsius is our guess, or that's the actual value. If our guess is 5, like this first guess we have, and the actual temperature is 0, then the absolute guessing error is 5 minus 0, which is 5. I show this as a point on the graph. Pause the video here and work through the rest of these examples. Hit play when you're ready to see an answer. Here is the answer to the warm-up. We can see that our dots make two straight lines and they have a vertex at 0, 0. Question number 2 asks, what rule can you write to find the output given the input? And there are a ton of different ways that you could have written this or expressed how you know. So here's a sample answer. Take the guess, whatever that number might be, and subtract 0. The sign of the value does not matter. So even if someone guessed 4 and someone guessed -4, they would still be 4 away on that guessing error. Absolute value is the big idea for this lesson. What is absolute value? It is a number's distance from 0 on the number line. So it is the actual distance that any number might be from 0. So for example, the absolute value of -4 is 4 because it is 4 away on the number line. We can write this in mathematical notation as what you see on the screen. So I will just call those bars. So another example would be what you see on the screen. I could say the absolute value of -4 is 4. That would be how I would read that example. In looking at page 235, we're going to continue to make a graph, and the function a tells us the distance from 0. So x is what we would think of as our guess, and then a of x is that absolute guessing error. So now we're just formalizing the absolute value definition. So your goal here, your task, is to complete this table and sketch a graph of the function. Now, this first example where x is 8, I know that that is 8 away from 0. So on my graph, I'll have a point at 8 for the guess and 8 for the distance from 0. The examples where it gives you the distance from 0, know that there could be more than one x value, right? If my distance from 0 is 5.6, that tells me that my x value could either be positive 5.6 or negative 5.6. They are both 5.6 away from 0. I'll have you pause the video here so that you're able to finish this graph and then move on when you feel like you're ready. So here's what your graph should look like when you've connected the dots. So this is the graph of the absolute value function. This is what I'll call our parent graph. In question number 2, Andre and Elena are writing different rules for absolute value functions. And we didn't talk about what Andre's rule looks like. That's what's called a piecewise function. But we can see Elena's rule where she writes the function as the absolute value of x, and that's what this is. On page 236, the activity is called moving graphs around. So here are some equations and graphs that represent 5 different absolute value functions. So I want to point out that some of them look like V's and some of them look like check marks, and that doesn't make a difference. What is happening here is just the window that we can see the graph. That's what's different. So focusing on this first graph, if you want to put a box around it on your paper, this is what I'm going to call the parent function. And this graph has a vertex or a low point at 0, 0. We want to know then what happens when we have different elements and we're using the number 2 here. What happens to the graph as we introduce the number 2? So I want you to do the following. Number 1, I want you to note how did the graphs change from the parent graph. So what's happening from the graph that's in the box to each of the other 4 graphs, like literally what is happening. Is it moving up, down, left, right? Is it flipping? Whatever. And then also identify what the new vertex is. That's going to be helpful for us to know. Pause the video here, and when you're ready to see the answers, hit play. Let's start. Our graph on the left is f of x equals the absolute value of x. That's our parent graph with a vertex at 0, 0. And the first graph we're going to look at is g of x, and that is equal to the absolute value of x minus 2. We can see that this graph shifted to the right 2 places, and our new vertex is 2, 0. The next graph we're going to compare is x plus 2, the absolute value of x plus 2, and this graph shifted to the left 2 places. This graph now has a vertex at negative 2, 0. The third graph we will compare is j of x is equal to the absolute value of x, and then subtract 2. And we can see that this graph changed from our parent graph to move down, and its new vertex is 0, negative 2. So it took our parent function and shifted everything down by 2. And our last graph is k of x, which is equal to the absolute value of x, and then we add 2. So this graph moved up 2 spots, and its new vertex is 0, 2. So in summary, and note that you should probably write this down, when we have any absolute value function, 2 things could possibly happen. If the number is inside the bars, that moves the graph to the left if it's positive, or to the right. So if it was x plus 5, the graph would have shifted to the left 5. And if it was x minus 5, it would shift to the right 5. The number outside the bars moves the graph up if it's a positive value or down if it's a negative value. Feel free to pause the video at any time and make sure you get the notes. Page 237 is a little bit more complex, where we're still moving graphs around. You can complete this activity on your own, and you're also welcome to use Desmos.com to help you. The absolute value symbol is above the Enter key on your keyboard. You'll have to hit Shift while hitting that key to get the symbol. Pause this video if you'd like, and your answers are available on the next slide. Here are the answers to the 14.4 activity. For problem 2, you had to create the graph. Hopefully you were able to show that the graph moves over to the side. And here is a list of some practice that you can/should be working on. This is all stuff that we've done since break. So we're talking about domain, we're talking about range, we're talking about inputs and outputs, and we're talking about absolute value graphs. I encourage you to work on a few of these problems. I'll have the answers for you when I return. Feel free to come back to this video at any point that you need. Thanks and have a great day.